Hello, everyone, and welcome to this explainer. Okay, we're going to just dive right into the deep end today because we are heading way out to the outer edges of our solar system to investigate the ultimate cosmic oddball. We are talking about Uranus. It's this massive, freezing, and just incredibly windy ice giant sitting billions of miles from the sun, all wrapped up in this serene-looking blue-green atmosphere of hydrogen, helium, and methane. But despite looking so calm on the outside, this planet hides a violently chaotic past that astronomers have been trying to decipher for decades. See, the true mystery of Uranus really boils down to one single, mind-boggling number, 97.77 degrees. Basically, every other planet in our solar system spins somewhat like a top as it orbits the sun, but not Uranus. Its equator is tilted at nearly a right angle to its orbit. I mean, it literally orbits the sun rolling on its side like a giant icy ball. And as you'll see, this extreme sideways orientation is absolutely crucial to understanding the planet's violent history. So the huge question here is what on Earth, scratch that, what in the solar system knocked Uranus on its side? How does a massive planet, the third largest by diameter in our entire neighborhood, end up completely toppled over? Well, today we're going to treat this explainer like a cosmic cold case investigation. We'll look at the timeline of the ice giant's life, the bizarre consequences of its current state, and the two major suspects. One is a long-held conventional theory, and the other, it's a fascinating new model that might just crack the case wide open. But before we investigate the cause, let's look at the wildly bizarre effects of being knocked entirely on your side. For starters, Uranus has the most extreme seasons in the whole solar system. Its poles experience 21-year-long completely pitch-black winters. And get this, when Voyager 2 flew by in 1986, it discovered a magnetic field that is just totally out of whack. It creates this lopsided magnetosphere that's twisted into a long corkscrew shape, stretching millions of miles behind the planet. And thanks to some recent 3D mapping by the James Webb Space Telescope, we now know this causes its auroras to sweep across the surface in incredibly complex ways. Oh, and to top it all off, it rotates in retrograde, meaning it spins backwards compared to most of the other planets. Okay, to solve our planetary mystery, we first need to understand the backstory, birth and outward migration. Just like the rest of the solar system, Uranus took shape about 4.5 billion years ago from a swirling disk of gas and dust called the pre-solar nebula. But unlike the massive gas giants, Jupiter and Saturn, Uranus and its twin Neptune just never accreted enough matter to hit that critical exponential growth spurt. They kind of failed to become massive gas giants, remaining smaller ice giants instead. Then, around 4 billion years ago, they migrated outward to the deep, freezing edges of the solar system. And it's roughly in that 3 to 4 billion years ago window where scientists think our major tilting event took place. This chaotic outward movement is perfectly explained by what's known as the NICE model. Basically, this planetary theory suggests that the ice giants actually formed much closer to the sun and were later kicked outwards by gravitational interactions into their current, lonely orbits. And this chaotic outward migration period, it is the absolute perfect breeding ground for planetary instability. Which brings us to Suspect 1, the giant impact hypothesis. So, the conventional thinking for a long time has been that early in the solar system's history, a massive Earth-sized protoplanet just violently smashed into Uranus. This single cataclysmic strike would have been powerful enough to physically knock the ice giant completely onto its side. And what's really compelling about this suspect is that it helps explain another weird anomaly. See, unlike the other giant planets, Uranus emits almost zero internal heat. A massive early impact could have essentially cracked it open, causing the planet to expel most of its primordial heat, which would leave its core surprisingly cold today. Sounds like a solid theory, right? Well, this giant impact hypothesis has one fatal flaw, and its name is Neptune. Uranus and Neptune are literal planetary twins. I mean, they formed at the exact same time, in the exact same environment, and migrated outwards together. So if the early outer solar system was essentially a chaotic shooting gallery of massive planetesimals, why did Neptune survive the exact same conditions completely unscathed, with a totally normal tilt, while Uranus got completely toppled? That discrepancy has always bothered astronomers. And that lingering doubt introduces us to Suspect 2, the phantom moon theory, based on some incredible cutting-edge research led by Melaine Cyanfest at the Paris Observatory. To understand this brilliant new theory, we need a quick primer on the physics of gravitational resonance. Essentially, as a planet spins, its axis naturally wobbles or precesses. It's exactly like a spinning top that's starting to lose its momentum. If a large moon orbiting that planet slowly moves further away, its gravitational pull can actually synchronize perfectly with that wobble. These perfectly timed rhythmic gravitational nudges can drastically alter the planet's rotation over time. Now, you might be thinking, come on, how could a tiny moon tip over an entire planet that is more than 14 times the mass of Earth? No way, right? Well, Silenfest's team ran the computer simulations and the data is pretty shocking. It turns out that a satellite with just 1/1000th the mass of Uranus could generate enough gravitational force to tilt the massive planet, provided the moon was migrating outward at a very specific rate. So here's how this silent tipping process happens, totally without invoking a single violent crash. First, in the early days of the solar system, Uranus hosted a large ancient satellite, a primordial moon that began slowly drifting away from the planet. Second, as it drifted, it hit that gravitational sweet spot where its nudges perfectly synchronized with Uranus's spin. And finally, over millions and millions of years, this constant rhythmic pulling gradually tipped Uranus further and further onto its side. It wasn't a sudden, chaotic crash. It was a slow, inescapable gravitational judo move. But wait, if this moon was just slowly pulling the planet over, why did the process stop precisely where it did? And where's this phantom moon today? Let's get to the climax, a fossilized spin axis. The simulation reveals a pretty spectacular demise for our phantom moon. Once the planet was dragged past an 80-degree tilt, that delicate gravitational dance completely broke down, making the satellite's orbit violently chaotic. Ultimately, the moon was thrown wildly off course and crashed directly into Uranus. And boom, with the moon destroyed, the gravitational pulling stops instantly, Uranus's behavior stabilizes, and its extreme 97.77-degree tilt is permanently locked in, or fossilized, exactly as we observe it today. I absolutely have to share this quote directly from the researchers because it really hits the nail on the head regarding why this model is making such waves. To our knowledge, this is the first time that a single mechanism is able to both tilt Uranus and fossilize its spin axis and its final state without invoking a giant impact. In science, an elegant single mechanism model that explains multiple weird phenomena without requiring a random catastrophic coincidence, that is highly prized. It cleanly explains the tilt and the stabilization in one continuous story. And the ultimate smoking gun evidence for this theory? It's sitting right there in the moons themselves. Uranus has an extensive system of 28 known moons, mostly small, icy bodies, but it noticeably lacks a giant primordial satellite. Meanwhile, its peers, Neptune, Saturn, and Jupiter, all host massive ancient moons like Triton, Titan, and Ganymede. The highly suspicious absence of a large moon around Uranus today perfectly matches the theory that it once had one, but destroyed it in that chaotic orbital climax. Of course, to truly confirm these incredible theories, we need better data. Uranus has only ever been visited once, by the Voyager 2 spacecraft during a brief solo flyby way back in January 1986. And while telescopes like JWST are currently doing just amazing work from afar, like mapping those complex auroras and tracking upper atmospheric temperatures, it's just not enough to fully map the interior or understand the intricate dynamics of its moons and rings. That is exactly why the recent Planetary Science Decadal Survey has proposed a new flagship mission, a dedicated Uranus orbiter equipped with an atmospheric probe. And that leaves us with a final provocative thought. If a single fleeting flyby decades ago revealed a lopsided magnetic field, 10 new moons, and a dark ring system, what in the world will a dedicated orbiter uncover when it finally arrives to stay? Will we find the ancient remnants of the phantom moon deep within Uranus's fluid mantle? Until humanity sends a spacecraft back to the sideways planet, this cosmic cold case remains open. Thank you so much for joining me for this explainer, and keep your eyes on the stars.